Okay, let's look at the section 9.5 continued. All right, here's the theorem. Let f be a function from set A to set B. All right, and f inverse. So this is an inverse relation, but this inverse relation happens to be a function from B to A, if and only if f is bijective. Right? So let's prove, since this is a if and only if statement, so we have to do both implications. Right? So let's try to write the proof for this implication. So if f inverse is a function, then f is bijective. Right? So first line. Oops. Right, first line. Right? So assume that f inverse is a function from B to A, right? So this is given. Right, line 2. Right, so let's show that f is 1 to 1 first. Right, so let's start with f of A 1 is equal to f of A2. Right, I'm gonna call that B, right, because they're just the same thing. Right, so this is given. Then we want to show that, in order to show that f is 1 to 1, we have to establish that a1 is equal to a2. All right, so let's do that. 3. All right, so using the inverse relation, if a1 maps to b by f, so inverse, so f inverse must map B back to A1, right? At the same time, since f of A2 is B, which means that the f inverse of B must be equal to A2, right? So I'm just using line 2 and using the definition of inverse relation, right? And line 4, right? Then we can use the fact that f inverse is a function, which means that if you plug in the same value, you have to get exactly the same thing. So which tells you that the a1 is equal to a2, right? So which establishes that f is 1 to 1. So this comes from the fact that f inverse is a function, right? So therefore, we establish that f is at least f is 1 to 1. All right. All right, let's try to show that it is onto. So maybe go up here. So line number 6. All right. So I'm gonna choose any arbitrary element B in the set B. All right. So this is given. All right. So since f inverse is a function on B, so 7, there exists an element A in A. It's actually a unique element such that f inverse of B is equal to A. right? So I'm just using the fact that F inverse is a function from B to A, all right? Hence 8, all right? By using the definition of inverse relation, so we know that there exists the same A in A such that, right, so F inverse goes from B to A, the original function, F of A goes to B, right? So this just using line number 7 and the definition of inverse relation. All right, so this establishes that 9, all right, so therefore, all right, F must be onto, all right, so I'm using, let's say, line 6 and line 8, right? Oop, I forgot to give a justification for this. So I'm using line 2 here and line 4. Right? And final conclusion is, so line 10, therefore, we know that F is bijective because it's 1 to 1 and onto at the same time, right? So justification would be combining line 5 and line 9, right? So this is the proof of this implication, right? Let's do the other implication. All right, so we're proving the other implication. All right, let's start with, all right, so we assume line 1, right? So F is bijective. Actually, I'm going to write F is 1 to 1, right? So that's given, right? Because it's bijective, and 2, and F is onto, right? So this is given, right? So in order to establish that F inverse is a function from B to A, we have to show that, let's see, so we want to show for all B in set B, there exists a unique element in A, in set A, such that F inverse of B is equal to dot A, right? So let's do that. So line number 3, we're gonna choose any element B in B, right? So this is just a given. All right, so we picked a random element B in B, right? So we have to show that there exists a unique element A in A such that the F inverse of B is equal to that, right? But since we know that F is onto, right, there exists at least one A in A such that F of B is equal to, all right, sorry, F of A is equal to B, right? since this comes from let's see, f is on 2, so no, let's see, 3, I'm using 2 and line number 3, right? And 5, right? So this shows that let's see, we have 5. We can rewrite this guy as there exists an element A in A, right? Right. So if f goes from A to B, then f inverse, it's just the inverse relation, goes from B back to A, right? So this is 4 and the definition of inverse relation, right? So we could show the existence, just existence, part of this proof, right? So we have to show that this A is actually unique, right? So let's come over here, 6. So let's try to show that it's unique, right? So assume that there exist a couple different A. So I'm gonna call it A1 and A2 in A, such that f inverse of B is equal to A1, right? At the same time, f inverse of B is equal to A2, right? Then 7, all right? Then we're going to rewrite it. So it's going to be f of A1 right is equal to B, right? And from here, just using the original function, so f will take you from A2 to B, right? So I'm using line 6, and this one, justification, there's no room here, so justification here, this one's just a given. All right, so assume that you know, there are a couple of different A's, then we want to show that it's actually they're the same. All right, so 7, line number 8, right? Since f is 1 to 1, once f of A1 is equal to f of A2, we know that A1 is equal to A2, right? So I'm using 7 and also 1 to 1, so it's 1 and line 7, right? So which means that we thought that the A1 and A2 are distinct elements, but turns out they're actually exactly the same element, right? So 9, right? That will establish that for all element B, or maybe I should say here, how about this? There exists, right? Before we could just say there exists an element A, but now we can say there exists a unique element A in A, such that the F inverse of B is equal to that A, right? So therefore, we could show that F inverse is a function. So therefore, F inverse is a function from B to A. Right? So this is a proof of the implication this way. If F is bijective, it guarantees that its inverse relation is a function from A to B. Sorry, B to A. All right, that's it. I hope that this was clear.